Okay, so for this video, we're going to talk about representing data graphically. And what I find is that for the most part, my students have seen this kind of data or this kind of graphing. And a lot of the types of graphs that we're going to talk about here, you've probably seen. You may not have thought about the pros and the cons of them. You may not have looked at the good, the bad, and the ugly. We're going to do some of that. Why this graph versus that graph, those kinds of things. But most people have at least seen some of them. However, there are a few graphs that we're going to talk about that are specific to statistics that a lot of people may not have seen before. So that's what we're going to do. The first one I want to look at, though, is the line graph. And lots of people, if I can write today, lots of people have done this. We use this in middle school and high school, and a lot of people have used these graphs. And in general, they start with what looks like a quadrant, what you would do in algebra with a quadrant, and a lot of times this would be the independent variable and this would be the dependent variable. And I'm going to talk to you about what kinds of things do we need for our graph and what kinds of things do we not necessarily need. So for a line graph, people a lot of times will say, oh, you put a point to represent each data point, or a dot. Sometimes people say dot, but we're going to call it a point. But we put a point and then we connect the dots, basically, is what a lot of people say. So that's how they keep this straight. Okay, and that is the idea of the line graph, so we'll see how that looks. Okay, but before I go any farther, I need to label and I need to know what I need to put in there and what I don't. So I'm using the data that we had in the last video about the length of our hands represented in large cubes. So that's this is the independent variable, number of large cubes. And then the frequency, or how often each one of these occurs, is going to be the dependent variable. Okay, so down here, give yourself a tiny bit of space here. Oh, I'm sorry, I need to label my graph before I do anything. I'm going to call this guy large cube frequency. Large cubes frequency. Okay. So down here, I need to talk about the independent variable. And normally, the bottom one here, the horizontal axis, is normally the independent variable. And I say normally because sometimes people twist them or turn them or whatever. But for our purposes, I'm going to call this the number of large cubes to represent your hand length. That's what that was. And like I said, give yourself just a tiny bit of space between the axis and where your label is, because we're going to have to put some numbers in there. Okay, and then going up, that's the frequency, or how often each of those occurs, if you'll remember. Okay, the frequency. But instead of putting that, I'm going to say number of people. I guess I can put frequency in parentheses so that everybody gets that great statsy word in there. Okay, but that's the number of people, and that's going to be vertical, so we're going to talk about that too. So I need to figure out how I'm going to label this axis. If you'll remember, on the number of large cubes here, we started at 6, because we said, well, we don't have any zeros. That doesn't make sense for us. That would be people without any hands at all. 1 or 2 is probably baby-sized hands or toddler-sized hands. 3 and 4 is probably kids in elementary school. I have had that one student who had a 5, but most of the time classes start somewhere around 6 snap cubes. So I need to start my labels in here around 6, and I need to go up to 13. And basically what I want to do, with the exception of this first gap here, I want to try to make sure that these are pretty evenly spaced. And I think everybody probably knows that, but I need to go all the way up to 13. Okay, so I want them to be pretty evenly spaced, but the question becomes, what about this? And so what happens is sometimes when we start out our data, either on the independent or the dependent variable, sometimes there's a gap. And I don't want to represent all that. You could put marks. This is 0 way down here, right? you could put marks for 1, 2, 3, 4, 5, and all that, but sometimes it takes a while, and I don't have space for that. Like if my data points hadn't have started until 130, well, I don't want to put 130 or even counting by tens or anything like that. So we use this little, I call it the lightning bolt, or it looks like a heartbeat on a heart monitor or something like that, the little lightning bolt thing. And what that does is that represents the fact that I've got a gap in my data. Okay. Now you can't do that in the middle. Okay. You can only do that at the very beginning to represent, oh, I'm not going to show you that there's a bunch of zeros in here. If I wanted to, I could have put 1, 2, 3, 4, 5, and there would be a bunch of zeros. We wouldn't have any dots at all, right? But I didn't want to do that, so I want to just kind of skip a space. Okay. Now going up, that needs to represent the frequency, or how many times I got each of those measurements. So I need to know about how tall I need it to be. Well, my biggest number on the frequency is a 7. You don't have to count by ones. I'm going to because it's just a 7. But if you wanted to, you could count by 2s or 3s or whatever. Sometimes I'll skip count, that kind of thing. But I'm just going to go 1 to 7 because I've got space for that. So here we go. 1, 2, 3, 4, 5, 6, 7. And again, I'm going to try to space those as evenly as possible. And again, if I hadn't have started until 5 counting these, like if my smallest frequency was a 5, I might have started here with the 5 and just put a little lightning bolt there to represent that I'm skipping stuff there. All right. What I don't want is I don't want to put a point at 0, 0 because there aren't any data points that were 0 hands, 0 people, right? So I'm not putting a point there. I'm just going to start with my first data point here at 6 cubes and 2 people, right? When we said 6 cubes, there were 2 people. So I'm just going to put a point right in there somewhere, okay? And basically, I think everybody probably knows, you've done this before, that I'm basically trying to find the point where those two meet. 6 snap cubes, 2 people. So I want to match that up as much as I can. Okay, so for 7, there were 3. That's somewhere in there. Get as close as you can. It doesn't have to be perfect. If you want to do kind of dotted things to make sure we know that they're matching up pretty well, you can. For 8, it was 5. So that's a little bit of a gap in there. So meaning that it got taller faster, basically. Okay. For 9, it was 7, which is going to be way up here somewhere. And again, you don't have to do the little dashy thing. I'm just trying to make sure my graph looks pretty good. For 10, it's 4. That guy's down here somewhere. And for each of these, I'm putting a point that shows how much frequency each of these has. Now notice I'm not putting a point for each person. I think I said this was Sally and this was Mary or whatever. So I'm not putting a point for each of those. That is actually a different kind of graph and we'll talk about it. Instead, I'm putting the total for each one. So we've got a 10 and a 4. I have an 11 and a 0. Now that is an actual data point. How many 11s do you have? I don't have any students that said they had 11. So I'm going to put a data point way down here. And then 12 is 2. And 13 is 1. Okay. So now if I'm looking at that and I'm trying to, it was a little bit tall. Yeah, something like that. Okay. If I'm looking at and I'm trying to, quote, connect the dots, which is what a lot of students tell me, then it's just going to be a straight line in between these dots, in between the points. And if you were thinking algebraically, then you might think about the slope of these little line segments that's in between each one of these. How steep is one versus the other? The one that just goes over 1, up 1, well, that one has a slope of 1, and it's very shallow, so to speak. But this one right here, it went from 4 down to 0, so it's over 1, down 4. That one's pretty steep, right? So if you're thinking along those kinds of lines, that's okay, because a lot of times algebra and stats and geometry, all those just tie together, right? And that's what's happening here. So, yeah, there we go. There's our line graph. Okay, What are the benefits of this one? Usually it's pretty easy to graph. Most students can read it pretty easily. You can go, oh, for instance, which one has the most? Well, 9 snap cubes had the most. There were 7 people. Sometimes it can be, as you saw here with the 1, it can be a little difficult to say, oh, is that a 1 or is that a 1.5 or is it a 2? If you're not exactly right. If you have grid paper, then it makes it easier to go up 1 over 1, that kind of thing. But so sometimes it can be a little bit iffy on exactly where I'm hanging out there. Okay, so that's a line graph. Like I said, most people have probably seen that, and it's all wonderful. The second kind, again, a lot of people have seen these, and so they're probably okay with it, and I'm not going to spend too terribly much time. But the second type is a bar graph. Okay, a bar graph. And basically, whenever we're talking about a bar graph, and I'm just going to throw one up here so we can see it, it consists of bars that represent frequencies, sometimes relative frequencies. So again, it's how often does this thing happen. Oh, let me do one for this so we can compare. So it ends up looking very similar. You have the 2 axes. You still need to give a label for the thing. Oops, sorry, there we go. Large cube frequencies. So it's still going to be the same data that I'm representing, right? So I'm going to do the same title, but this one's going to be a bar graph instead of a line graph. I still need to label my axes, so I'm going to say number of large cubes on the independent down here, and on the side to side, or the up and down, I'm going to say number of people. And again, that means frequency. How often do I have each of those? And probably I'm going to have a very similar look to my labeling on this, right? Because it's the same data. So again, try to space them as evenly as possible, 6 through 13 on the bottom. I went ahead and put in my little lightning bolt thing there to let everybody know that I'm skipping. If you wanted to, you could count by 2s over here or something like that, but I'm trying to compare these, so I want them to be as similar as possible, so I'm going to do that. Okay, now here's the difference. There's a couple of things that we should note about bar graphs. First of all, if we were in class, I would do this kind of like a Post-it note activity. So I would have you come up here and put a Post-it note. Oh, mine is a 6. And then somebody else, Susie could put her Post-it note on the 6s. And then Mary could put her Post-it note on the 6s. And I'd make sure that we all had the same size Post-it note and that we could line them up. Okay. So for the 6s, there were 2. And so that one would be 2 bars high. Now the thing to notice is that if I give everybody the same kind of Post-it notes, then what? We all get the same width and we all get the same height. So basically, every person's data is worth the same amount. Okay? So that's kind of the way I think about bar graphs. So think about Post-it notes, if you would. Everybody gets the same size Post-it note. Then Susie's vote is worth the same as Mary's vote. That's what I'm saying. Okay? So they should look pretty similar in the bar. Okay? Now, you don't have to do individual squares, in fact, I won't. But what I should do, as much as I can, hopefully, is I should have these Post-it notes or these bars centered on whatever the label is here. So for 6, I need 1 bar, and it needs to be this 2 units tall, and I'll go for there. For the 7, it should be 3. It should be centered on the 7, and it should be 3 units tall. Okay, I think this first one's a little wide. The 8, centered on the 8, 5 units tall. Again, I'm not going to belabor this. If you were splitting it up, there would be that like that, but it doesn't have to be. It can just be one big thing. The 9, centered on the 9, is 7 units tall. The 10, centered on the 10, is 4 units tall. Okay, what about that 11? There was an 11-0. There aren't any. So what about here? I hope that you're saying, don't make a bar. There's nothing there, right? So we don't represent that one at all. I have seen some books. The 12 is a 2. And the 13 is a 1. All right. I have seen some books that put just a little flat thing there. You're welcome to do that if you want. But basically, you don't have a square, right? So I don't put anything there. Okay. So I've got this kind of thing going on here. And it's making a nice, pretty graph. I can definitely still tell that the one that happens the most often is 9 cubes in this class, right? It has the most votes, or the most people, number of people that had those was 9 cubes had 7. That's the biggest number in my chart for frequency, right? Okay, comparing these two, I think you'll see that in the line graph, the 11-0 is a lot more obvious, maybe, than in the bar graph. Also, lines are easier to draw, in my opinion, than bar graphs are, like the bars. Bars are very easy to read, and a lot of people really like these, and we use them a lot for elementary and middle school because they're easy for kids to pick up on because they're more solid. Like how tall this is very obvious. So that's what's going on there. Both of those very, very popular in some of the math classes, so I'm sure you've seen those. One of the ones you may not have seen. Okay, let's talk about that. The ones you haven't seen, there's something called a Pareto graph, or a Pareto chart. Okay, well, what the heck's that? Well, that's a bar graph, but it's arranged in order. From highest to lowest, or sometimes it's lowest to highest, but for the Pareto, you're going to start at the highest and go lowest, okay? So for ours, that doesn't make sense, right? Because I would have had to put the 9 down here and say there were 7 that were 9s, and then the next biggest one would have been the 5, so I would have put an 8 next, and then the next biggest one would have been this 4, and I would have put the 10, and then the number of cubes would be all out of order, right? 9, 8, 10, 7, 6 and 12 are side by side, and then 13. It doesn't really make sense in our data, right? But it happens a lot for qualitative data. So for instance, which vehicle do you like the best? The Volvo or the Ford or the Dodge? Okay, so the one with the highest rating would come first maybe, and then down past that. So qualitative data happens a lot more. You'll see it for that. Let me show you a difference. So first let me show you the difference in data for a bar graph versus a Pareto. Okay, this is the 5 largest U.S. cities: Chicago, Houston, Los Angeles, New York, Philadelphia. Okay, nothing at all wrong with that bar graph. Okay, they happen to be in alphabetical order: Chicago, then Houston, then Los Angeles. No particular reason. Okay, but here's the same data, the same graph, but it's rearranged highest to lowest. Okay, so if we're talking about the 5 largest U.S. cities, it might be smart for me to put the largest one first, right? The highest value. So New York, then Los Angeles, then Chicago, then Houston, then Philadelphia. So that's one of the cases where it's not wrong to put it as a bar graph, but the Pareto might make a little bit more sense for us to use it that way because we're talking about largest. So it just kind of lines it up for us. Now notice that the cities are not in alphabetical order, but we don't really care, right? Who cares if Chicago is listed before Houston? I don't care. Or whichever one. Okay. Here's another example. Total carbon monoxide emissions. Again, this is some qualitative data that's going on there because we're talking here, well, it's not, it's quantitative because I've got numbers going out there. So how much emissions is there in the China, in the United States, in India. So we see here the largest first, China, then the U.S., and so on. So that's who's letting out the most CO2, right? Okay. Now this one's interesting, per person, looking at it. So per person, United States was second here, but per person, we are first. We have the highest rate of carbon monoxide, or carbon dioxide, sorry, emissions. Okay, CO2. Okay, then Russia, then South Korea, then Japan, then Germany, then Iran, then China's way down here. Okay, when we looked at it earlier, these, 8 countries or so, it was first, and it does put out the most. It's, if you were to ever go to, say, Beijing, it would be smoggy, 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 because there's a lot. But it's so much in one location, so to speak, because they're packed into one spot, if that makes sense. So there's a lot more people there. So when you spread it out per person, it's less emissions per person. So that's why they're way down here. India was third in emissions up here, but they're per person the last of this group. So that's interesting data. So sometimes it makes sense to make it, to rearrange your data in a Pareto chart just so we can see that kind of comparison going on. Okay, what else? There is something that's similar to these Paretos and bar charts and stuff like that, and it's called a histogram. And what I've noticed is that sometimes it's not difficult to know the difference, but sometimes people get mixed up, so to speak. So a histogram is a bar chart, bar graph, and it has quantitative data. So that is one of the ways that it's going to be different from the bar graph. So the bar graph can be quantitative data, but like I just said a second ago, a lot of times you'll see it's qualitative data. What's your favorite color? What's your favorite place to eat? Whatever, okay? So those are more qualitative, and they have individual bars like this, okay? So there's that. But the interesting thing is the bars are touching. Okay, they have a set width, and the width normally means like 1 unit or 5 units or whatever, but all of my bars are the same width like they are in the bar graph, but the bars are touching. And why does that happen? Okay, a lot of times we're dealing with continuous data, which happens with quantitative, right? Or it can happen with either the interval or ratio data. Okay, so for instance, if I've got something and I know that, let's just say, I don't know, test scores, okay, test scores, because we did an example of those on the last video, right? If I was looking at test scores, then I might say the way that they had them broken down in that one example was 70 to 75, 76 to, what was it, 79? It was 70 to 74, 75 to 79, that's what it was, 80 to 84, and so on, okay? So if I made my histogram looking at that kind of thing, and this would be test scores. I'm not going to really make a histogram here. I just want you to get the idea. I've got, actually, I think I have an example of this. Hang on. Yep, I do. So let me just pull one up so you can see it. All right. Here we go. All right, so 70, 75 on the scores, okay. If there were 4 people in that group, the reason why we come way up here, a lot of times, the reason why the histograms touch is because if we're talking about continuous data in particular, I want to be able to get right up against the next bar, if that makes sense. So for instance, somebody who made a 74.9 is in this first bar, right? But it comes right up against this 75. So I want them to be touching, because as soon as it hops over to a 75, I want to go to the next bar here, okay? And if you're in a 79.5, well, you're still in this bar, but as soon as you hop over to an 80, I want you to go up to the next bar. And so we end up seeing that kind of thing going on, especially for the continuous data. But quantitative in particular, you should have some kind of nice natural order to it. And whenever we're talking, for instance, here on test scores, that does have a nice, pretty order. So that's good. And since they have it here, I'll talk about it. See how they've got the difference here between the two? We can see this is the histogram. This guy is the line graph, right? Okay. So those two side by side, we see, okay, what's going on there? We've got all the same data going on, but some people are going to like the line graphs better, and some people are going to like the histograms better because they can for sure tell this is a 7. Here it might be hard to see that that's a 7. We can see the plateau better here maybe, but we see that these are the same. So it just depends on how you want to look at it. Sometimes you'll need specific types of graphs for certain things. Okay, so that's a histogram, and you'll see more of those as we go through. A lot of times, as we go through the semester, a lot of times though, you just remember the histogram is going to be used when we have the quantitative data, when it's normally going to come out. Okay, how about a dot plot? This one's a little weird to me. I don't use it much, I don't see it much, but I want to make sure that you've seen it. So again, I'm going to use the data that we had from our large cubes. Okay, so this one's kind of close to a line plot, I guess, because it's got the dots in there. So that's what makes me think of the line graph. Everything looks the same whenever I'm labeling my axes, putting in my scale here, number of large cubes. If for some reason you had a reason to do something weird, you might have a legend going on, a key, an answer key, so to speak, but we don't have anything weird going on here, so I don't feel the need for it. Okay, one more time with this particular kind of data. Well, one more time after that because we're going to do pie charts, but yeah. One more time with this particular data. The interesting thing about the dot plot, and a lot of times you'll see this whenever you're taking measurements on a population and you want to see where data points accumulate, so to speak. So what we've got here is for the 6. We know that we had 2 people, but basically it's a matter of I want to represent both of them. So Susie gets a dot and Mary gets a dot. So everybody gets a dot. Okay. For the 7, we had 3. So instead of just coming up here to the 3 and putting a dot to represent the total height for that 7 cubes, I put one for each person. So basically every person we have gets a data point. Okay, so 8 was 5, 9 was 7, 10 was 4, 11 was 0, 12 was 2, and 13 was 1. Okay, but I can't just do what I did on the line plot. Instead, I need to fill in a data point for every person. So whenever I look at 9 had 7 people, I should have 1, 2, 3, 4, 5, 6, 7 dots on that particular line, so to speak. So 10 had 4, so 1, 2, I got off a little bit. 1, 2, 3, that's not a point here, 4. Sorry. Okay, something like that. 11 had 0, 12 had 1, 2, and 13 had 1. Okay, so it kind of looks like I'm building on top of myself a little bit, but basically, if I do it this way, then I can come back and check myself because I should have what? 24 total dots. So that's kind of nice because I don't lose the total in this guy like I would if I did the line. And like I said, the line graph can fit right on top of this, right? You can see it right there. So we had that one, the line graph. We can see it right on top of that. But we don't put in the line graph for the dot plot. Sometimes we can say, we'll call it an overlay or an overlap of the line plot or graph. Sometimes we'll see that, and in fact, whenever we get to talking about the normal graphs, a lot of times I will overlay and we'll talk about that. So, yay. All right, so dot plots, they're out there. What else? Pie charts. I'm not going to waste your time with pie charts, but that is a type. Normally in this class, what we're going to do is we're going to read a pie chart. So let me give you an example, and we'll talk about what's going on here. Okay, this one's easy enough. Here's a pie chart. It talks about registered voters in Rochester County. I'm sure everybody has seen a pie chart before, so I'm not going to belabor it too much. People registered Democrat, 25%. People registered Republican, 25%. People registered Independent are 50%. Okay, that's a pie chart. The problem with the pie chart, and I'm just going to let you know, is that you need percentages. There's no actual data points on here, no raw data, okay? With everything else we've had, like the dot plot, we can look at it and we can kind of say, oh, there's 7 people who had a 9, okay? How many people are Democrat? Oh, we don't know. Sometimes there will be a little legend out here that'll tell me the total number of people surveyed is, like, if it was 100 people, then that would be 25 people Democrat, 25 people Republican, 50 people Independent, right? If it was 20 people, then I'd need to split that into 4, so 5, 5, and 10. So we can sometimes regain some of that data if they give me a total somewhere, if I have that as a legend or something, but, and a little key over here. If I have that, then great, but a lot of times these pie charts don't tell me that kind of thing. So here's another one. Exam grade data. Well, the A's are 16%, the B's are 28%, the C's are 36%, 12% D's, and 8% F's. So that's all fine and dandy, and it's really nice. What the pie chart is really good for is comparing. We can see, for instance, that there were a lot of C's. And when we look at D's and F's, we can tell that most of the people in the class passed, like 75-ish%, maybe more, okay? But again, I don't know how many people that is, okay? I just don't know what is 16%, like what was the total, how can I find? So we have to work in percentages, and that's kind of the problem with a pie chart, is if all I have is raw data, first I have to change it into percentages and work with it. So for this class, we're not normally going to do that. Normally what you would be doing is reading data off of a pie chart. All right. That's most of what we're going to look at. There are a couple of other weird ones, like the time series graph. I'll show you an example of that. It's pretty obvious what that one is. The time series graph. Here's an example of one of those. Okay, death rate per 1,000 people population, and this is in the U.S. Okay, historical U.S. death rates per 1,000 people. We see that in 1900, there were about 16 or 17 deaths per 1,000 people, right? So that lets me know what's going on. We see an interesting trend where it's mostly a downward trend, where when we get to about 2015, there's only, say, 8 people, maybe, per 1,000 that are dying in that year. Okay, so it's definitely a downward trend. We can also see an interesting spike that's going on here around 1917, 1918. And the book that I'm looking at here actually asked the question, if somebody told you that that was from World War I, would you believe it? Well, that's about the right time for World War I, so that could have some impact on it. However, it's not that, and we can tell there's a tiny little blip here in the early 40s. That would be World War II, right? Right in there. But what about Vietnam here in the late 60s and early 70s? Again, just a small little bump up, but not really. There should be some stuff in here in like the late 90s, 2000-ish for the war, 2000s, I would say, for the wars in Iraq, and then further up here leading to Afghanistan and stuff like that, Desert Storm and Desert Shield and all that. So we see just a little bump there, but it's not this spike that we see here. It's a definite spike. So what the heck's happening around 1917, 1918? Well, what actually happened there is that was the introduction of what they called at the time the Spanish flu. Okay, we now know it just as the flu, basically, but there was no vaccine for that particular virus at that time, and so it's actually one of the greatest death rates in America, and basically it was about 850,000 people who died from the flu. Now, part of that could be linked with World War I, because they said that actually one of the biggest killers of men in the trenches in World War I was the flu. So because they were in such close contact with each other, if you got the flu, you were likely to spread it to your buddies, basically. Okay, so yeah, it was a huge one. 20 million people worldwide died of that flu. So big one right there. But you can see how the time series graph goes, right? It's year by year, or it could be month by month, that kind of thing. All right, there's actually two more big ones that we're going to talk about. Stem and leaf and box and whiskers. These are actually more modern. They were created in like the 70s and 80s. But I will save those for another video, and I will do them together, just those two. So this, I think, what we've covered so far is just a basic look at graphical representations of data. And like I said at the beginning, probably you've seen a lot of those, but some of them, like the Pareto, the time series graph, the dot plot, those might be unusual for you, and there's probably some homework on some of those, so make sure that you're aware of them and you can use them. All right, if you have questions, let me know. Thanks.